All right, guys, this is statistics 5.2, and we're going to be talking about binomial distributions today. So to start off, what does that mean? So binomial, by meaning two, right? It means there's two possible outcomes for us. Now we're typically going to define those as a successful and a failure one. So a success is what we want to happen happens, and a failure is what we want doesn't happen. Now, this can have a bit of a weird connotation to it because people will typically look at success as being a positive thing and failure as being a negative thing. But it can be the case of I'm looking at cancer rates, right? And if someone ends up having cancer, that is a success in my experiment because that's what I'm looking for, right? It doesn't mean it's a good thing that it happened. It means that that's what I'm looking for. So you need to kind of get your head out of success is a good thing and failure is a bad thing for this context here, right? Because this is the terms we end up using. So a few variables you want to be aware of. N is going to be our number of actual trials. R is going to be our number of successes. P is going to be the probability of a success, and Q is going to be the probability of a failure. So when we talk about what a success is versus a failure, in general, a success is what you're looking for, and a failure is not what you're looking for. So anything else falls under the failure state there. Okay, so let's take a look at some of these examples. So the first one here is about blood types. So about 9% of people have type B blood. So we're going to do an experiment with 18 people and figure out, well, what percent of them have type B blood, right? There's a little note here. I'll explain what that means. Since we're taking 18 people, blood type is a thing which is passed down genetically. So if I pick two people or multiple people in the same family group, that could throw off my results, right? Because I could, like, if I pick everyone from the same family and they all have type B blood, that's going to drastically change my results versus me getting a truly random population. So since 18 people out of the entire population of the US is very, very small chance of them being related, we can assume that it is random. So that's kind of what that little note there means. Okay, so let's go through A, B, C, and we'll do this one together. So in this experiment, we are observing whether or not a person has type B blood. We will say that it is a success if a person has type B blood. What is a failure? It's anything other than type B blood, right? They could have A, they could have AB, they could have O, any of those, right? So then the probability of success is 0.09. What's the probability of failure? Well, failure is anything other than a success. So if I do 1 minus 0.09, I'm going to get 0.91. Right, so 0.91 is going to be my probability of failure. And then how many trials are in my experiment? Well, I have 18 people, right? And then I'm looking for the probability of me getting 3 successes out of those 18 people. So that's going to be what my R is. Now those are the variables you want to be able to define in order to do these types of like problems. Now we really haven't gone over how to do these types of like problems. That's where we're going to head next. So before I do the one with the blood type, we're going to do one here with a much more simple case, which is just so that you can kind of see what's going on, and then we'll apply that to the blood type case. So let's say we have the last 3 problems on a multiple choice test, and we're just going to be randomly guessing on those, right? We're going to try and figure out, well, what's the probability of getting some number of things correct here, right? So if you do a tree diagram here, right, we end up seeing that you could get all three right. The first two right, the last one wrong. You could get then right, wrong, right, wrong, right, 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 wrong, 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 right, wrong, 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 right, wrong, wrong, wrong. Those are our 8 possible cases. Again, you could draw out the tree diagram and get all of those. And then, but if I then say, well, what's the probability that this happens, right? Well, in order for me to get a success, that's going to be 0.75 times 0.75 times 0.75. Now let's get out my document camera. So the success is 0.75 times 0.7, sorry, a success is 0.25 times 0.25 times 0.25. Because I have a 1 in 4 chance of getting the first one right, 1 in 4 getting the second one right, 1 in 4 getting the third one right. So my probability of getting all of them right is going to be 0.0156. Right, or 0.016 if we round to 3 places, right? Well, what if I wanted success, and failure? Well, that's 0.25 times 0.25 times 0.75, because right, wrong. Well, that's going to be 0.046, which makes sense. You're more likely to get one of them wrong than to get all 3 of them right from purely guessing, right? And I could do that for every single one of those. And if I do that, that's where this ends up coming from, right? I get these probabilities here. Well, a lot of these are the same outcome effectively because the order doesn't really matter here, right? Kind of like a combination, right? So I can say, well, all 3 of these cases are effectively the same. They are all me getting 2 successes, right? So if I add up all of these, I have a probability of getting 2 successes of being 0.141. Right? Then my probability of getting only 1 success is one of these 3 cases. So if I add up all 3 of those, I get 0.422, right, which is a pretty high chance. And my probability of getting all 3 wrong is also 0.422. So I have the same chance of getting all wrong as getting 1 right. And then getting 2 right can happen, but pretty rare, and then getting all 3 of them, probably pretty low chance of me actually having that happen. But again, it is still possible, right? So that's this is what I would actually care A about, right? Is these numbers here? What's my probability of getting one of these 3 problems right? Well, you got about a 42% chance of getting one of them right, which is decent, right? So that's kind of how this works. So what we just did there, if you think about it, was oops, I change. There we go. Okay, is we did this, right? We took the probability of a success and multiplied it by itself the number of times we needed a success. Then we also multiplied that by the probability of a failure, the number of times you needed a failure. Right? So what that looks like over here, oops, wrong. I had 2 successes, so I could have said this. Well, this is 0.25 raised to the second power times 0.75, my failure raised to the first power, right? Which is what this is saying. Success raised to the number of times you want a success times failure raised to the number of times you want a failure, which is why it's n minus r, is because that's going to be the number of times you fail if you get a success r number of times. Right? And then, well, what's this NCR stuff? Like, why am I doing a combination here? Well, again, back to that example we just did, right? There we go. That's me saying, well, this, and this are effectively the same, and there's 3 of them, so it's just one of these times 3, right? And that's what that NCR is actually going to do for us. That NCR is going to multiply by how many times you get that same thing, just in a different order, right? So that's going to be our equation for finding the probability of successor. So let's take a look back at our blood type problem, right? So we are looking for 3 people to have type B blood out of the 18, right? Our probability of success is 0.09. Our probability of failure is 0.91. So if I go to some paper and try and do this out, I would say, well, I need, my N is 18, so that's 18 combination 3, that's my NCR, times my probability of success is 0.09, and I need that to happen 3 times. So that's raised to the 3rd power. Then my chance of a failure is 0.91. I need that to happen every other time. Well, that's 18 minus 3 ends up being 15 times that I need a failure. So that's all I got to do, right? Go to my calculator and type all that in. So if I do 18 combination 3, that times 0.09 to the 3rd times 0.91 to the 15, and it being 0.144558, etc., right? Which ends up being our probability of getting exactly 3 people that have type B blood, right? So now let's take a look at this problem here. Okay, so go ahead, pause the video, try this out. It's the same thing we just did, just in a slightly different scenario here. All right, so we end up seeing that in this operation here, the success rate is 30%. And the NA team of surgeons has developed a new way of like doing it that has been a success 4 out of 6 times, right? So is it likely that the new technique is better than the old one, right? So let's define our variables here, right? So our N, our number of times we're going to be running this, is 6 because we have 6 people in our trial. Our probability of a success, if we're using the old metric, is going to be 0.3, right? And then 0.7 for a failure here. And then we have 4 people that were successful. So this feels a bit weird, right? Because you're saying, well, why am I using the probability of success from the old rate, right? And that's because we don't have good data as to what the new success rate is. And you may say, well, it's 4 out of 6. Duh, because I had 4 people and 6 in trying. Well, that's a super small sample size. You cannot be saying that this is valid. So what we're trying to do is say, well, let's assume it's still following the old technique, right? What's the chance of us getting 4 good and 4 good out of 6 just at a pure random chance? Because if that's super low, then hey, there's probably a good chance that this has a higher chance of being working than others. And that's kind of how we actually find probabilities, right? It takes a lot of time and experiments to get, hey, there's a 30% success rate here, right? You can't get that off of 6, 7, 8, 9, 10 people. You need hundreds, if not thousands of people to get a good, solid rate there, okay? So once we have that, right, let's compute the probability of getting 4 successes exactly, right? Well, that would be 6 NCR 4, right, times I need 4 successes, so 0.3 raised to the 4th power, times 2 fails, so 0.7 raised to the 2 power. And then you should end up getting 0.060, right? So that means that, hey, this happening out of pure chance, right, is 0.6, or sorry, 0.06 or 6% chance of it happening, right, which is pretty rare. But that's not the only thing which we actually want to use, right? What we actually want to find is the probability of having at least 4 successes, right? Because maybe this is actually a kind of bad batch, right? And this new technique is really good. Like it's like an 80% effective, and I kind of got a bad batch with my 4 out of 6, right? So I also want to look at what the probability of being 5 successes and 6 successes. And then I want to add all of those up. So that's what I'm doing here, right? If I do the exact same thing as I did for the probability of 4, but do it with 5, well, that's 6 NCR 5 times 0.3 raised to the 5th power times 0.7 raised to the 1st power. Could be because I want 5 successes and 1 failure. Then I get that probability there. Then do the same thing for the probability of getting all 6 of them right? So that's going to be 6 in CR6, which, spoilers, is 1, times 0.3 raised to the 6th power times 0.7 raised to the 0 power, which raising it to the 0 power is just 1, so it doesn't really do anything anymore, right? So if I add up my probability of 4, my probability of 5, and my probability of 6, that's my probability of getting at least 4 successes, and that ends up being 0.071. Okay? So this is the kind of result we want, right? So if I said, hey, there's only a 7% chance that this is happening out of random chance, the other 93% chance is that this new technique is better. That's effectively what we are saying based off of these results here, right? So that's a pretty good indicator that this new technique is better. Now, is that a guarantee? No, right? Because there is a 7% chance of it happening. 7% is not 0. So those rare cases can still happen. But if you had to bet, you'd probably bet on, hey, it's probably better than the other technique. All right, so that's effectively where we're kind of going forward today. If that problem made sense and you're able to do this kind of equation here, we're in good shape. Okay, all right, here's our assignment for 5.2, doing 1 through 4, and then 5 through 31 is just the odds. And I will talk to you guys next time.